Hello everyone, welcome to our sixth topic in our unit on dynamics. This is going to be a two-topic in a row kind of lesson. We're going to do a lesson, topic 6 on universal gravitation, and I'm going to make a YouTube video for this one. And the reason why I'm going to do that is because I want to make sure the lesson after this, the one on gravitational fields, is one that I do as a group. Basically my logic is I'm going to make a YouTube video as the intro lesson, and then we can kind of follow up with any questions you have and kind of summarize this two-topic. Like they kind of go together, right? Like one is going to lead right to the next. That's why we're hopefully doing topics 6 and 7 on back-to-back days. So anyways, that's the rationale. We're going to do this one by a video, and then the next one's going to be done as a group lesson. Really, these two lessons are the second half of our unit. The first half of the unit is all about Newton's laws, as well as a discussion about friction. And so we should have done 3 lessons on Newton's first, second, and third law, and then on friction. The second half of our unit now is all about gravity. We want to discuss basically the force of gravity and discuss one new formula that goes with it. And then tomorrow we're going to talk more about gravitational fields and how that concept works. So anyways, let's get started here. What I want to do is I want to begin with just reminding you of Newton's 3 laws again. And so hopefully you're familiar with his 3 laws by now. One of them involves a math formula. Newton's first law is all about inertia. Newton's second law is basically one of the few formulas we're learning this unit, which is F net equals ma. And Newton's third law is the equal and opposite reaction law. And then after that we talked about friction, which is one of the main forces that you'll encounter. But the other main force that we're going to work with is gravity. And so, pardon me, Newton, just like he was working on his 3 laws of motion, one thing that we didn't mention beforehand, but he was working on these 3 laws with the attempt to try to explain gravity. The legend, you've probably heard it, goes that Newton was, sitting under an apple tree and an apple hits him on the head, and he has this big eureka, oh my goodness, I figured it out moment. And I'm not sure that was actually true or not. But that's really, that was Newton's goal. He was trying to work on trying to understand gravity. And we're going to talk a little bit about gravity in Physics 20, and then we're going to talk about some other forces that are similar to gravity in Physics 30. There are actually 3 forces that are very similar, and they're all known as action at a distance forces. That's the phrase we use, action at a distance. Those are action at a distance forces. And they're actually very similar to, gravity is very similar to 2 other forces. One involving magnets, and the other one involving, I should have written this nicer, electrostatics. And what makes these ones that's either. What makes the gravity similar to both of these is that these are forces that exist, and things do not have to touch each other. The opposite of action at a distance forces are contact forces. And contact forces, for example, would be something like friction, where friction only happens because 2 surfaces are in contact with each other. But gravity was something hard for Newton to explain because unlike when I throw something or when friction happens, he could explain that because 2 things were directly touching each other. Gravity happens over a distance. If I just let go of an object, it falls and there's literally nothing touching it. And that's basically where we want to begin our lesson here, is the idea of Newton is trying to describe and explain how gravity works. Now, before I kind of move on that, I want to remind you what Newton's third law was. And Newton's third law was all about the action-reaction forces. I like this top picture. I think this one makes a lot of sense here. Where when a person wants to, say, push off of this wall right here, right? There's a surface right here. When a person wants to push off of this wall right here and launch themselves when they're swimming in one direction, really there's 2 forces happening, right? There's a force of the wall on your feet and the force of your feet on the wall. And so, I mean, clearly this person's feet are trying to push into the wall. But what ends up happening is if the wall doesn't move, the wall is going to push the person back, and that's really what allows you to propel yourself. And the same thing happens if you're like swimming. If you pull the water behind you, the water pulls you forward. And so those are basically action-reaction forces. And the reason why this matters, I have one more slide on this. This is again Newton's third law. If you push on the ground pushes on you. Well, what Newton realized is that although this was still action at a distance, there were action-reaction forces due to gravity. And once Newton clued into this, he was able to piece this together. Now, this actually is something that that does not make intuitive sense to us, because when we think of gravity, we think of there's the ground right here, and we think of an object. I'll just make it a box, and we just think of, well, what's really happening is gravity is just pulling this object down. But what Newton realized is that, just like with every other force, including our contact forces, that there must be an opposite force as well. And he realized that there must be a force of gravity where the Earth is actually getting pulled up towards the object that's falling. And that makes no sense. I better say that again. We all recognize that the force of gravity pulls an object down, right? This object right here that I'm coloring in purple, we all recognize the force of gravity is going to pull it down. But what Newton realized is that this object right here is also causing the Earth to get pulled up. And we don't notice that because the Earth is just so massive that we don't actually see the Earth actually getting pulled in an upwards direction. All we notice is the object that's falling. We notice it falling. But Newton hypothesized that there must be an equal and opposite reactionary force in the exact same way that when you push on the ground pushes you. Or if you push on the wall pushes you back. If I can go back to the slide right here, eventually Newton concluded that a gravitational force exists between any two masses, both being attracted to each other. And so I don't think that the apple falling on his head really represented Newton discovering what gravity really was. He finally realized, though, that what was really happening is that the apple, let's use this apple right here. This apple right here, he realized that gravity, yes, the Earth was causing a force of gravity pulling the apple down. But I think the eureka moment was him recognizing that the Earth was actually getting pulled up towards the apple. We just can't see it because the Earth is so massive that it moves like a fraction of a millimeter compared to how far the apple moves. And that was really groundbreaking. It's not something that maybe you even right now as you're listening to me, you're saying, Chris, you've got to be lying to me. The Earth is not actually moving. But I mean, Newton's third law, that this was the logical extension, is that every force must have an equal and opposite reactionary force. So we got a few slides to kind of illustrate this, I believe. This is the main slide right here. So let's go back to this one. The Earth is pulling a person down. But in the same way, the person is actually pulling the Earth up with the exact same amount of force. And we often talk about how that needs to be the normal force. And that's not really what I'm discussing in this scenario here. There will be normal force. The normal force well, I mean, I guess in this scenario maybe we could consider it that. Maybe let's describe it that way. Earth is getting pulled, this object is getting pulled down by the force of gravity. But in the same way, as long as it's resting on the surface of the Earth is actually, the normal force is pushing it back up. I think we get that when there's an object literally sitting on the ground. But what we're now saying is that if there was an object that wasn't sitting on the ground, if the ground is way down here, the same thing still applies though. If there is a force of gravity pulling this object down, the Earth itself is actually getting pulled up by the same force of gravity. Yeah, crazy, right? That was Newton's his hypothesis. And so let me go to this slide here. Newton hypothesized then that any object which has a mass is gravitationally attracted to every other object having mass. And that was the force of gravity. And so basically what he suggested is that the larger the masses of the object, the larger the gravitational forces. Another way of describing this is that he suggested that there is a direct relationship between the force and the mass of an object, the gravitational force and the mass of an object. If you have more mass, there is going to be more gravitational force, which kind of makes sense. If you have a larger object, there's going to be more force of gravity. As an example, imagine that you dropped a pencil on your foot from 3 feet above the ground. And then you dropped a bowling ball on your foot from 3 feet above the ground. Well, they're both going to fall at the same speed. They're both going to accelerate at the same rate due to gravity. But the bowling ball could break your foot because it has more mass. And if it has more mass, it has more force due to gravity. Now, here's something that's kind of cool is that hundreds of years later, when man finally went to the moon, this was confirmed because hopefully you know this, but on the moon there's a less gravitational force. And this also made sense because the moon has less mass than the Earth does, right? And so I found this little picture right here. Bit into the Earth. And so therefore that's going to change how much the force of gravity is when you're on the moon rather than when you're on Earth. So, I mean, if you've seen photographs or videos of astronauts on the moon, they kind of bounce a little bit. You can jump a lot higher because there's less gravity there. So, now, I've got a lot of notes here that we're basically reading. We'll get to the math examples in a bit, but this was really key. This meant that each object has a mass that is the source of its own gravity. Basically, what it suggests is that every atom in the universe is attracted to all the other atoms in the universe. And if you've ever watched or seen documentaries talking about the Big Bang Theory, that's actually the theory behind how matter started clumping together, is that after the Big Bang there were particles, and they were all scattered throughout the universe. And that's basically what caused all these particles to start attracting to each other, is that there is a force of gravity attracting these molecules, and these ones, and those ones, and those ones. And it's a two-way force, so if this one's attracted that way, this one's attracted back. And eventually matter started clumping together, and really that clumping together of matter is what eventually turned on our stars, because fusion reactions were able to take place as gravity basically forced molecules closer and closer together, thereby fusing them. So I like this diagram right here, because I think this is the one I was thinking of earlier, where what ends up happening is there is a force of an attraction between the apple and the Earth. We normally just think of the apple as getting pulled down, but the Earth is getting pulled back up again. There's also a force of attraction, though, between an apple and a person. However, the amount of gravitational force is much less. Right here, the apple and the Earth were by basically about 1 Newton, give or take. But the gravitational force of attraction between an apple and a person is way less, because the person that's involved doesn't weigh nearly as much as the Earth. The only reason why we even notice gravity is because of the fact that that the Earth is so massive. If we lived on a planet where that planet itself was not that large, we would hardly even notice gravity. Like if we lived on the moon or a smaller planet like Mercury, we wouldn't even notice gravity all that much. In outer space, there isn't any gravity whatsoever, right? And at least like gravity that we're used to. There is gravity, but we're going to talk about that with centripetal motion later. So, as kind of a funny anecdote, I've got a friend who would always say that he's the most attractive person in the room, gravitationally speaking. He was kind of a large fellow, and so he always used to joke that he was always the most attractive person in the room, and gravitationally, kind of making a play on the words that if you have more mass, you have more gravitational attraction. Right? So that's what I've got written down here, is that every mass pulls on every other mass. But objects aren't always being pulled together due to gravity, and the reason why is that if masses are relatively small, and to be honest, you and me and even my friend who is kind of large, I mean, even if you weigh 200-300 pounds like my friend did, I mean, you still don't actually have much gravitational attraction that we notice it, and friction will definitely be enough to overcome that, and so it'll prevent this apple from actually being sucked into this person's body. But the larger something is in terms of mass, the more gravity there is. Like I said, Newton discovered basically this concept here. If I were to draw basically a graph here, Newton discovered that there is a direct relationship between the force of gravity and the mass. Increase how much mass there has, and gravity is going to have more force on it. It's actually one of the reasons why it's so hard to launch objects into outer space. There's actually a bit of a paradox there, is that in order to launch objects into outer space, you need to give them a lot of fuel. And when you give them more fuel, it increases their mass, so their mass increases. But when you give them more fuel, and it increases their mass, then it means that the amount of force of gravity on them goes up, and therefore you have to work harder to escape Earth's gravity. And if you have to work harder to escape Earth's gravity, you need more fuel, which then means you need more mass, which then means you're heavier, so you have to escape larger gravitational forces. And it's a vicious cycle. So there's actually kind of a happy medium when you're trying to launch a rocket into outer space as to how much fuel you need, because the more fuel you provide, the heavier you are. The heavier you are, the more gravity works on you, and the harder it is to launch something into outer space. So, okay, let's move on here. I've actually got outer space kind of as an example here. Objects don't just fly towards each other, is that the distance between objects impacts the gravitational force. We're going to focus more on gravitational attraction of celestial bodies in our next unit. But, I mean, if you were to imagine, like, say, the gravitational force in outer space, one of the reasons why there really isn't any is that you're so far away from Earth. Distance also has an impact. The further the distance away, the less the gravitational force. There is actually an inverse, oh, I can't even spell it, inverse, I-N-V-E-R-S-E. There's an inverse relationship between the amount of gravitational force you have and the distance the two objects are from each other. And so the further you are away from the object, the less gravity there is. There's this graphical relationship, a reciprocal relationship. And so that's actually what explains this picture right here, is that objects in outer space, they really aren't subject to much gravity because they're too far away from Earth for gravity to be effective. The further away you get, the less gravitational attraction there is. So, here's kind of a graph that kind of illustrates this, is that if we were to talk about your distance away from Earth's center, if you're basically right on the surface of the Earth, which is one radius away from the center of the Earth, then gravitational force of attraction is basically 9.81. And so that's what basically is being measured right here. This is basically at 9.81. But as you get further and further away, if you go into outer space, the further and further away you get, the amount of force that Earth has on you gets to be very minimal, to the point where it's hardly even noticeable. And yeah, I mean, objects in motion will then stay in motion, but the amount of force that you have is pretty small. So this would be known as a reciprocal. This is a reciprocal graph. And those of you who are doing or have finished Math 20-1, you might recognize this as being the graph of y equals 1 over x. It has an inverse relationship, where if you increase this number right here, it actually decreases this value here. So that's what I have on this slide right here. What Newton basically then started to piece together is that there was a direct relationship between gravity and the masses. If you increase the mass, you increase gravity. And that's basically what this little statement shows. This little symbol right here, it basically means proportional. And so what it means is that gravity, the force of gravity is proportional to the masses. If you increase the mass of objects, you get more gravity, which helps explain why, again, since the mass of Earth is so massive, even when our masses are pretty little, you get a decent amount of gravity. But if you were to talk about the gravitational attraction between you and the cell phone you're watching this on, you and your cell phone are pretty small. There's really no force of gravity between you and your cell phone. So the object has to be fairly large. There's actually an inverse squared relationship. I kind of skipped over that on the previous slide. But what Newton discovered, it wasn't a true inverse relationship. It was an inverse squared relationship, where basically what happens is if you take a distance between two objects and square it, and then find the reciprocal of that, that's how much force there is. So, for example, let's say that you actually had a distance that was 1, but then you've increased that distance to 2. That's actually what this R stands for. R stands for kind of like the radius between objects. Radius and distance are often used interchangeably in many of these formulas. So if you ever see D or R, they really refer to either the distance between objects or the radius between them. And the reason we use the word radius is that, say you have object 1 right here, object 2 could be here, or here, or here, or here. It really doesn't matter where its location is. Anywhere within like kind of a circle, anywhere within that circular region will still have the same force of gravity. So, anyways, back to what I was describing here. Imagine you had a distance that was 1 and now you made it 2. Well, what would happen is if you made this number right here 2, the force, which used to be 1, would now become 1/4. That's basically how this relationship works, is that if you double the distance, you would then make it 1/4 as much for force. Or if you were to say triple the distance, it would now become 1/9 the force. Or if you were to quadruple the distance, it would become 1/16 the force. That's what Newton basically discovered. And so he began to piece together a formula. And I probably have this on a future slide, but what he basically discovered is that if he pieces together a formula, that gravity is equal to 2 masses being multiplied, because there's always 2 objects that contribute to gravity, and we have to then divide it by the distance between them squared, which is either represented by R or D. Either one's valid. But what he was stuck with is when he did those measurements and took 2 masses and divided by a radius, it didn't quite work. And so he discovered that he had to put a constant in here. And we haven't worked with constants a whole lot yet, but there are many constants in physics, which probably are best described as numbers that kind of do just enough to alter an equation to make the numbers fit under all circumstances. And a constant is a number that basically it's always the same number. It's always 5, or it's always 7, or it's always 4.32. And so you can change the mass up or down if you want. You can change this mass up or down. You can change this radius up or down. But what Newton discovered he needed was a constant in order to kind of make the math fit so that whatever this letter here, let's call it A, and this one here B, and this one here C, that it always managed to equal this side over here if you times it by the same number every time, that constant. Newton's struggle was that to try to figure, well, what is this constant that I need to multiply by? So before I get to that, let's just do a quick few more summary slides, and then we'll talk about how they solved this problem here. So again, I like this picture here. It says gravity acts between all objects. But if you use a bigger object, the force of gravity increases. But if you use a bigger distance, the force of gravity decreases. Basically, this is your direct relationship. This is your inverse relationship. This one means add more mass, you get more force. This one means add more distance, you get less force. And so this again led to basically where Newton finished off. And Newton finished off with him summarizing, saying, here's a formula for universal gravitation. I believe that I can always predict the force of gravity, and I can predict it if I know 3 variables: the mass of the first object, the mass of the second object, because there always have to be 2 objects that have gravity between them, and then the distance between them, which we often use as r standing for radius, because we don't really care whether it's east, west, up or down, left or right, so we can kind of consider it to be in a circle around the object. But what he was lacking was his constant value, basically like you have to multiply by a certain number so that it always works out just to fit perfectly. Like I said, we're going to learn about many constants as we go on in this course. This is the first one we're learning about. So now, on the back of your data sheet, it actually tells you what this constant is. It's 6.67 times 10 to the minus 11. And eventually this was figured out. But I have a little note on the slide here. You don't actually have to memorize this constant value. It is on the back of your data sheet, along with many other known constants. For example, you might see Planck's constant on there. Or you might see, what other constants are there? There's the constant for what an elementary charge is on the back of your data sheet. So there are many known constants in physics. This would be one of them. Right now might be a good time, if that's not making sense, to pause the video and ask me in person to elaborate a bit more. But I have to now spend a little bit of time discussing, well, how did we discover this constant, which is 6.67 times 10 to the minus 11? Where the heck did this number even come from? And this didn't happen until much later, when Henry Cavendish managed to figure out a way to discover the universal gravitational constant G. And he set up this really intricate experiment. And so I've got a few different slides that are really just pictures of the exact same thing. And so what I can do right now, if you'd like, is I can explain it over this picture, as well as this picture, as well as this picture. I got 3 different pictures here, and they all kind of involve the same thing. So here's what Cavendish did. He set up a mass on 2 different sides here, attached to a piece of wire, say, hanging from the roof. And what he discovered is that if you put really large masses in the close vicinity, what would happen is this mass right here, the purple one, and this mass right here, the green one, they would then start to have a force of gravity attracting them. Now, it wasn't a lot, right? I mean, we know that unless the masses are the size of the Earth, the force of gravity is pretty minuscule. But he realized, and he knew according to Newton's research, that these 2 things would start attracting each other. However, the only one that could move was the one that was hanging from this wire. And so what he was able to do is measure the radius between them. He was able to measure the masses between them. And he was able to figure out the torque on the wire. And by that I mean he was able to figure out how much this wire bent. And then I believe the first time he did it, he had predetermined how much torque measured compared to a force. And so he had previously twisted this wire. And so if it twisted like 1 degree, then it needed to be 1 Newton. And if it twisted 2 degrees, then it meant it was 2 newtons. And what he was essentially able to do is fill in all the remaining variables. He was able to know the mass of one object because he weighed it, the mass of the second object because he weighed it. He could measure the distance between the objects, And this force right here, he knew what it was because he had predetermined how much twist there was in the wire as to how much force it took to make that twist. And it basically meant that the only variable left in this formula was this previously unsolved for constant of g, and he was then able to solve for g, which was kind of cool. And so I've got a few pictures that kind of describe it better. Before I get to them, though, Cavendish published his findings in a paper called Weighing the Earth. And I'm going to come back to that in a second as to why he called his paper Weighing the Earth, because you might think, what does that have to do with anything here? But I'll come back to that. So here's another example of the scenario. He's got this wire, and this wire right here, if there's an angle that this wire here bends, right, it used to be over here, and then it moves a little bit due to the force of gravity. As it bends, he measured the angle, and he already had a chart that he had already plotted out where if he used 1 Newton, he could make it bend, say, 2 degrees. And if he used 2 newtons, he could make it bend 4 degrees. And if it was 3 newtons, he could make it bend 6 degrees. So he already knew what angle required what force because he previously measured that. Then he brings the big mass and the little mass close together, and he measures the radius between them. And then he figures out how much it bends due to the force of gravity causing these two objects to come close to each other. Once he knows all of the remaining variables in Newton's formula, so here's Newton's formula, and again, Newton didn't know what g was until Cavendish figured it out for him. But once he knew what both masses were, because he could weigh them, what the radius was, because he could measure distance between objects, and once he knew what the angle was, which gave him force, he could then solve for the one remaining variable. Now, if that makes sense to you, that's awesome. If not, maybe pause the video and call me over for some clarification. But this is how a modern experiment works. It actually involves lasers and mirrors, basically. Rather than having a pre-measured amount of torque being based on how much like the wire twists, now what we do is we just put a mirror right here, and the mirror is on the object that can kind of rotate. And so as this mass goes towards this mass, as this mass goes towards this mass, it's going to cause this free hanging one, really both of them are free hanging actually, it's going to cause them to rotate towards each other. And what ends up happening is a light source shoots a laser in at a mirror, but then as this thing right here rotates, the mirror rotates a little bit, and over here where the laser ends up at, it moves slightly. And so as this mirror just slightly adjusts where it's at, now all of a sudden the laser hits over here. And using some pretty fancy trigonometry, they're able to figure out how much the angle was, and then using the angle they can do the same sorts of thing. They can then figure out just how much force there must have been. So they can do it much more efficiently now. So, anyways, that's known as the Cavendish experiment. It is one of the most monumentally successful and important investigations in probably Earth's history, because once we were able to figure out the missing number, the glue, that's a good way of putting it, the glue that held Newton's formula together, then they were able to basically make this thing fit. Maybe one more word on constants before I move on. We're only just starting to get to this idea, but like Einstein was famous for them, where he had all these equations, and he knew that like this thing, if it went up, this one went up, and he knew that if this one went up, this one went down. And so he was able to like piece together many formulas, but the math never worked unless he added a constant to the formulas to kind of like adjust the numbers. And if you always adjusted them by the same ratio, then it worked. And so that's basically this g, this constant is a ratio that adjusts so that things fit. So now I want to go basically to an example here, which was basically the whole point of Cavendish's experiment. Cavendish ultimately wanted to figure out the mass of the Earth. Now, if you look on your data sheet, if you can find it, there actually is a spot where it talks about things like the radius of the Earth, the mass of the Earth, things like masses of protons and electrons. I believe it tells you the mass of the Earth somewhere on your data sheet. But one of the cool things about it is that we can't actually put the Earth on a scale. It's not like we can take the Earth, put it on a scale, and say, oh, that's how much it weighs. But physicists, they wanted to know how much the Earth weighed for years, because they thought, well, clearly the Earth is made out of matter. I'd like to know how much it weighs, but they were stumped by the problem. Well, all of a sudden, now Cavendish had a way of solving it, because really he could then figure out the force of gravity. He knew that the force of gravity was equal to big G, I often call it big G, the constant which he just solved for, times the mass of two objects that are being used, all divided by the distance between them. squared. Now, one of the unique things about this is that this is one way of solving for gravity. But Newton had already discovered a shortcut, and we have discovered it as well. There's another formula for gravity, which is that it's just mass times the gravitational amount. And this gravitational amount of 9.81, it had been discovered experimentally over and over and over again, and so scientists were fairly confident that they knew that the force of gravity, the field strength, we're actually going to talk about how this is a field strength tomorrow, but they knew the field strength of gravity was 9.81. But they only did that because they just replicated experiments over and over and over again and discovered that acceleration of gravity was always 981. But this didn't account for the fact that there were always two masses and a distance between them. And so what Cavendish decided to do is basically make the two formulas equal to each other. So he then made the big G formula. That's what I call this the big G formula. And I like to call this one the little g formula. He made them equal to each other and said, well, they both are different ways of measuring gravity. So what I can do is I can make these two equations equal to each other. Well, then he realized, but hang on, I can cancel something on both sides, because there are two objects in this formula causing gravitation. One is whatever object it is that you have. As an example, let's make this an apple. This will be an apple. There's an apple with a leaf on it. Okay. And then there's the Earth itself. And the apple is getting pulled down to the Earth the same way as the Earth is getting pulled up. And so under the previous way that we solved this example, we just took the mass of the apple. Let's just call it 10 grams. And 10 grams, we do 10 grams times by gravity. But in the big G formula, we'd have to use 10 grams for the apple times by the mass of the Earth, which until this point they didn't know the mass of the Earth. But the cool thing is that this mass right here and this mass right here are both really the mass of the same apple. And since you have the same variable on both sides of an equation, you can cancel it. Which means the only thing that's left is M2, right? This one right here was M1. This was the mass of the apple. The Earth itself is M2, Earth. So basically what ended up happening was he could now solve for M2 by rearranging the formula like this. M2, which is the mass of the Earth, would be equal to little g times by r squared all over big G. Now, we know little g. Little g is 9.81. It has been experimentally tested that the acceleration due to gravity on Earth is 9.81. We also know now, according to Cavendish's experiment, that the big G constant is 6.67 times 10 to the minus 11. But the only thing we're missing then is the radius. What is the distance between the two objects? Now, you might say, well, doesn't it matter whether I hold the apple 3 feet off the ground or 4 feet off the ground? But what Newton realized is that gravity really depended on the center of the object. It really depended on like the center of the Earth, which is why we often use r for radius, because this is often the radius of the Earth. I mean, the radius of the Earth is so large that if you're an extra 3 feet above the surface of the Earth, it really doesn't matter. And so this radius right here was actually Earth's radius, which had been previously discovered. And so we actually know what this value happens to be. The radius of the Earth, I believe, is 6.37 times 10 to the 6. And you should be able to find this constant also on your data sheet. I mean, if you have your data sheet nearby, hopefully you'll see that there's the constant of the acceleration due to gravity. There's the gravitational constant. There's the radius of the Earth. Now, I should point out, you might wonder, well, how in the world did they figure out the radius of the Earth? How did they figure out how far the Earth was from here? And that's actually kind of a cool story. Maybe I'll explain that one to you in person if you care as to how they discovered that. But mathematicians actually knew the radius of the Earth for a long time. Really, if you know the circumference of the Earth, the whole way around the Earth, you can actually find the radius if you know the formula c equals 2 pi r. And since they had a way of measuring the circumference of the Earth, even though they didn't actually need a tape measure to literally go all the way around the Earth, the mathematicians have actually known the radius of the Earth for quite a while. So at this point in history, the radius of the Earth was known, and so all Cavendish had to do then was take the constant for gravity, which was discovered experimentally, times by the radius of the Earth squared, and divide by the big G constant he just discovered. And this allowed him to calculate the mass of the Earth, even though Earth itself is way too big to ever, I mean, you can't put it on a scale, right? That makes no sense that you could weigh the Earth by putting it on a scale. But he was basically able to discover that the mass of the Earth was 5.9679, etc., E24. And that would be in kilograms. And so I managed to calculate this by using this formula here. And if you look on your data sheet, it actually says that the value for the mass of the Earth is 5.97 times 10 to the 24 kilograms. That's on your formula sheet if you can find it. It's in the section on the backside called constants. And yeah, this was groundbreaking because now a physicist had now figured out a way to literally weigh the Earth. Hence the name of the paper by Cavendish, where he published his findings in a paper called Weighing the Earth. This is groundbreaking. So, okay, we're going to get into some math examples in a second here, but if you have any questions, this is another reason why I like to do this lesson asynchronously, is that if I teach this to the whole class, I often get a lot of funny looks where kids are like, what did you just talk about, Chris? First you told me that the Earth moves towards me when things fall. Like that's right off the bat, that's a bit strange. And now I'm talking about constants and new formulas. So now is a great time to ask me for some help. But if you feel like you get it, let's try a couple of examples here. So let's try the first one here. Mount Logan is 5,959 meters above sea level. What we'd like to do is calculate the weight of a 55 kilogram person at the top of a mountain. And I've put this example in here purposely because you might say, Chris, isn't the person going to weigh 55 kilograms? Isn't that a weight? And the reason why I threw this one in first is I need to teach you some proper physics terminology. I've got a slide here to describe it. Mass, density, and weight are all different things. And unfortunately, we use the word weight often improperly when we talk about how much our mass is. Mass is how much matter is in an object, and we weigh mass in grams or in kilograms or in pounds. And so if you are putting yourself on a scale and saying, I went and weighed myself, it's unfortunate that we use that terminology because you didn't weigh yourself, you actually found your mass. Your mass is how much of you there is. Okay. Density, although I didn't discuss density in this slide here, density is about how much mass you have per volume. That's basically how thick something happens to be. Lead is a very dense material. But if you're using the word weight appropriately, weight from a physics perspective is actually based on the force of gravity on an object. Weight is actually how many newtons something involves based on mass times the gravitational constant. And so what ends up happening is if you actually put yourself on a scale and you give yourself a mass, you've actually found your mass. But a weight is what happens when in physics, we use the word weight to describe how many newtons something is, which is basically mass times gravity. So if I can go back right here, if I ask you how much something weighs on the top of Mount Logan, this number right here is actually its mass. Its weight. What I'm really doing in a fancy way is asking you, what is the force of gravity acting on this thing? Now you might think, well, hey, why can't I just use the formula for the force of gravity? Mass times gravity. Why can't we just take 55 and times by 9.81? But the reason why that's not going to work, I got to cross that out, is that you're on top of Mount Logan, which means that imagine you're on the Earth right here, and you're right here. On the surface of the Earth, gravity is 9.81. But if there's a mountain that you go to the top to, this is a mountain right here, and now you're on the top of the mountain, gravity actually works a little bit less the further away from the center of the Earth you are, because we now know that the further the distance away, the less gravity there is. So we can't use the little g formula anymore. We have to use the big G formula. And I'm often going to use that as the shorthand way that I describe the two ways of doing gravity. There is the little g formula, which is mass times gravity, which only applies if you're on the surface of the Earth. And there's the big G formula, which is big G m1 m2 over r squared. And the reason why we call this formula something different, we call it universal gravitation. And the reason we call it universal gravitation is that this discovery allowed physicists to start to figure out masses and gravity on other planets without us actually having to go there. We've never been to, say, Jupiter or Saturn. Well, I mean, we have now. Probes have gone there. But before that, they knew how much gravity there was, because once they knew the universal gravitational constant, they could actually work with that, and they could actually solve problems. So that's why they call it the universal gravitational constant, because this can be applied anywhere that's not even on Earth. Now, the reason why this matters is if I want to try to calculate this weight right here, I now need to use the big G formula. which will be 6.67 times 10 to the minus 11. That's the constant Cavendish discovery. And then we'll need the mass of the two objects. Well, the mass of the two objects, one of them weighs 55, and the other one weighs 5.97 times 10 to the 24. Because this is the object of the person, and this is the Earth itself. The person is causing gravity just as much as the Earth itself is. Here's why the radius matters, though. We need to know how far apart the person at the top of Mount Logan is compared to the center of the Earth. And here's how this is going to have to look. We're going to have to take the radius of the Earth, which was 6.37 times 10 to the 6, and we're going to have to add an extra 5959 meters to it before we square it. The reason being is that if this is the Earth, and from here to here is the distance from the center of the Earth to the edge of the Earth, well, you're a little bit higher up when you're on top of the mountain, so we have to add more distance. And what ends up happening is if you increase your distance, it's then going to decrease the amount of gravity that it normally would be. So you can't just take this number and times by 9.81, because gravity is probably not acting at 9.81. It's probably acting at like 9.6. So anyways, if this makes sense, I'm going to get an answer for us here. It's 6.67 times 10 to the minus 11. We're going to times the gravitational constant by the mass of the person, 55, by the mass of the Earth itself, 5.97 times 10 to the 24. We're going to divide it all by, in brackets, the new radius. It'll be the radius of the Earth, 6.37 times 10 to the 6. Adding on an extra 5959, because that's how big Mount Logan is, and then all of that gets squared. And I have a final value of 539 newtons of weight. This is how we describe weight, which is going to seem weird because you're like, what? No, weight is how heavy you are in terms of mass, but mass and weight are actually different in physics. It's unfortunate that we've kind of gotten into the habit of saying we weigh ourselves on a scale. And the reason why we actually started doing that is because the way a scale works is when you step on a scale, imagine this is a person stepping on a scale here, right? What a scale is really doing is a scale is measuring how much force of gravity you have, and then it's actually dividing by 9.81. And when it does that, it gives you a mass value. And so what a scale basically does is it measures force. It's autoly calibrated to divide by 9.81, and then it tells you how heavy you are, which is why we call this weighing yourself, because you're actually finding the force of gravity. That's what it's actually doing. It's just no one wants to know how many newtons they weigh. They want to know how much mass they are. Okay, hopefully that made sense. I'm going to move on to the next example because I'm already up to 40 minutes here and I want to wrap this up pretty quick. So if you have questions, you have to call me over. Okay, please do not keep watching this video if that didn't make sense. But let's move on to I got 2 examples left, I believe. Yeah, 2 examples left. So let's try an outer space example because this was now kind of cool. Once Cavendish discovered the universal gravitational formula, they were then able to start making some discoveries about how much other planets weighed, how far apart they were, all of these numbers. They started being able to do way more equations. And so here's just kind of a silly little one. Let's figure out how much force is acting on this planet Io based on Jupiter, which is the planet it normally travels around, and the Sun. And I gave basically in this chart right here some distances and some masses of how far it is from Io to the Sun and how far it is from Io to Jupiter. And so I've got some numbers here for us to use. Let's try this example, because what we really have is a force of gravity 1, that Io is being attracted to the Sun, but there's also a force of gravity 2 where Io is being attracted to Jupiter. And I'm going to subtract these values from each other to figure out how much net force Io is actually undergoing. And so let's do this here. So I'm going to find Fg1. This is going to be G m1 m2 over r squared. And the way it's going to work is it's going to be 6.67 times 10 to the minus 11. We always use that number as the constant, which kind of made the numbers all fit together perfectly. Then we need to multiply by the mass of one of our objects. So let's go with the mass of Io. So 8.93 times 10 to the 22. Then let's multiply by the mass of the other object, so that would be the Sun, which is 1.99 times 10 to the 30. And then let's divide this all by the distance between them, which, as you can see in the chart, is 7.98 times 10 to the 11. But we got to square that. So give me a second. I'm going to grab my calculator. We're going to find out how much force of gravity the Sun and Io have on each other. And I bet you it's not going to be as much as you think it is because they're just so far away from each other. That's really the single biggest problem, is although they're relatively large objects, they are a long ways away from each other. Alright, and so I calculated this much force. I got 1.86 repeating times 10 to the 19 newtons, which is actually still pretty considerable. But that actually makes a little bit of sense because there is a force of attraction of the Sun keeping Earth and other planets from flying into outer space. We're eventually going to discuss that that actually is a centripetal force that's keeping everything from basically flying away, and that's what keeps us rotating around the Sun. So there is a certain amount of force that attracts us to the Sun. I'm going to store this as letter A, and like I said, I got 1.86 to the 19. Now I've got to find the force of gravity number 2, which is honestly the exact same formula. It's 6.67 times 10 to the minus 11 times by, what do we got? Now it's going to be the distance to, no, we still need the mass of Io, so that's still 8.93 to the 22. But now Io is being attracted to Jupiter, which only weighs 1.90 times 10 to the 27. And then when I divide by a distance, I need to know the distance from Io to Jupiter, which is 4.22 times 10 to the 8, which will square. So one thing you might notice is that Io doesn't, well, I mean, Io weighs the same in either example, right? But in this example here, the Sun weighs more than Jupiter does. However, the distance is less. And so let's see how this affects the mass values right here, or the force values. 6.67 times 10 to the minus 11 times by 8.93 times 10 to the 22 multiplied by 1.90 times 10 to the minus 27. We're going to divide this all by 4.22 times 10 to the 8 squared. And I ended up getting, ooh, I made a mistake here. Hang on. I need to go back and try that again. There we go. I used minus 27. Divided by 4.22 times 10 to the 8 squared. Okay, hopefully I didn't make a mistake here, but I got 6.35 times 10 to the 22 newtons, which I'm going to store as B. So what had more force of attraction? Was it Io being attracted to Jupiter or to the Sun? And it was Jupiter, which explains why Io actually goes around Jupiter first, but ultimately all of these objects actually go around the Sun as well. So we're going to talk about that more in a future unit, but this does kind of make sense. Now for our last step here, I just need to subtract these numbers. So I'm going to take B and subtract A. But one of the cool things you're going to discover about that is if you take these two values and subtract each other. Oh, I didn't actually store that one as B yet. Hang on. Let's store that one as B. Okay. Now I'm going to take B and subtract A. When I subtract these numbers, I still end up getting 6.35 times 10 to the 22 newtons, which kind of makes sense because the amount of gravitational attraction that the Sun has on Io, yes, there is some, but it's nowhere near as much as the amount of gravitational attraction Io has to Jupiter, which explains why Io is a moon of Jupiter. But since there still is gravitational attraction between the Sun and both Io and Jupiter, it's why they go around the Sun as well, which is kind of cool. So, okay, hopefully that made some sense. If it didn't, again, ask me some questions. I want to finish off with one more explanation of constants that I thought of, and then the last thing I'm going to do is give you an example for you to try. A lot of times kids ask me, Chris, why the heck are there these constants here? And one of the reasons why is that we have arbitrarily on Earth decided what to make a kilogram and what to make a meter. When you think about the units, this is a kilogram unit, and this was a unit in meters. And really, it's kind of arbitrary. We just randomly said that about a meter stick is what a meter is. But why couldn't a meter have been like smaller than that? Why couldn't a meter be the size of, like from here to Calgary? Or why couldn't a meter be how far it is from your forearm to your, like the size of your forearm? For the longest time, our units, our metric units, in order to keep them standardized, there literally used to be like a stick and a weight in a museum somewhere. And if you wanted to know how much something weighed, you had to compare them to the samples. And so there was a stick, and the stick was the official meter stick. Like, you know how we have meter sticks in school? Well, there was an official meter stick for a long time. And the official meter stick basically told you if you wanted to know what a meter was, you had to like check your meter stick against the official one in the museum just to make sure you were measuring meters properly. And same thing with weight. A mass, I shouldn't use weight, I should use the word mass. A mass of 1 kilogram, if you wanted to say, well, I believe this thing is a mass of 1 kilogram, you had to compare it to the actual mass that was in a museum somewhere, like I think it was in the Louvre for the longest time. Now, we've actually found better ways to measure things. Now time is actually based on how much the speed of light travels. And so we found more accurate ways to make it work, so you're not always comparing to like a certain stick or chunk of metal in a museum. But anyways, I think that helps explain why we have to have constants, because the units that we randomly chose to measure in don't always fit perfectly, but there's always like some sort of constant number that does make the numbers like just meld together perfectly. And so those are constants. So anyways, maybe that helps explain constants. Okay, my video's at 50 minutes. I'm going to call her quits here. Here's where we're going to finish. I've got an example for you to try. Okay, and so basically what I'm going to do is I'm going to give you a radius of the moon. I'm going to give you a mass of the moon. I'm going to give you the same thing for Earth's radius and Earth's mass. And I want you basically to calculate the gravitational force for someone who is on the moon, and then the same force for someone who is on the Earth. And I want you to try to explain why the amount of gravity on the moon is less than the amount of gravity on the Earth. And so what you basically need to do is use the FG, the big formula, twice. You have to do it once for Earth. You also have to do it again for when you're on the moon. And you're going to discover that the same 100 kilogram astronaut has a different weight on the moon. They have less weight on the moon. They still have a mass of 100 kilograms, but you ever heard the phrase that they're weightless? They have less weight because of the fact that there's less force of gravity. So why don't you try this one here? And what we're going to do here is I'm going to begin tomorrow's class with this example. And then tomorrow I'm going to do a group lesson on this final topic, gravitational field strength. And we're going to continue discussing this. And so that's why I chose to do this video asynchronously, is so that basically what I could do is I could intro you to the topic. You'll have some questions, I hope. Lots of people usually have questions on this topic. So you can ask me some questions. And then tomorrow I'm going to wrap up our unit, actually, with basically the second half of our gravitational set of 2 lessons, topic 6 and 7. So, okay, that's it for the video. Make sure you ask me some questions. Thanks so much, and we'll talk soon.